I'm making this video because, as a former geologist turned science journalist, when I've tried to explain the Earth's history during discussions on my channel, people seem to be very confused about timescales and how all this happened. So in this video I am going to show some basic geological principles and how they relate to the Earth's journey through the last billion years. I'll answer questions like, why is there so much oil in the Middle East? How did geology help in the hunt for Osama bin Laden? How does this age fit into the Earth's history? What causes changes in climate, and are there any cycles and patterns in all this? Let's first travel back through time to our starting point about a billion years ago. The Earth is a lot older than that, and we can find rocks going back over 3 billion years. But a billion years ago is when things start getting interesting. We'll call this dawn 5 o'clock in the morning and end our journey at 1 o'clock in the afternoon, the present time. Then we'll go forward in time and see what will happen to the Earth 250 million years into the future. So each minute will represent about 2 million years. By the time we get to our starting point, the Earth's protocontinents have already been moving around for hundreds of millions of years, and a billion years ago most of them were joined into one supercontinent called Rodinia. The Earth's crust may be solid, but on a large scale it's very flexible. It's made of a number of plates, driven around by currents of molten rock in the upper mantle. Where thinner and denser oceanic plates made of basalt were driven against thicker and lighter continental plates made of granite, the denser plate got subducted. When that happened, the edge of the continent buckled and molten rock from the descending crust rose to form volcanic mountain chains. When the subducting oceanic crust ran out, the continents themselves would collide and fuse, throwing up mountain chains. Basalt and granite fit within one of 3 rock classifications: igneous rocks, in other words molten rock that's cooled and solidified. Where it cools slowly, the crystals have time to gravitate together, forming large-grained rocks like granite. Where the rock is cooled quickly, the crystals don't have time to grow, so they are quite small, forming fine-grained rocks like basalt. A good rule of thumb is that the larger the grain size, the deeper underground and igneous rock has formed. Rhodonia lasted for over 300 million years. There was no life on land, just clusters of single-celled organisms building structures called stromatolites in shallow seas near the shoreline. About 750 million years ago, Rhodonia began breaking apart. The sea that opened up between North America and Australia became a dumping ground for sediments that would later get uplifted by another tectonic collision, forming most of western Canada and the northwestern United States. This brings us to our first geological principle, uplift and erosion. Land masses get lifted up through crustal movements, then eroded through processes like chemical weathering. This reacts carbon dioxide in the air with silicates in the rocks, and the eroded material is washed out to sea to form calcium carbonates, the main ingredient of limestone. It's an important process for the climate because over time it sucks carbon dioxide out of the air. Some of this limestone gets dragged down through subduction and melts, pumping CO2 back into the air through volcanoes. Fortunately for us, a lot of this carbon dioxide remains locked up in limestones today. There's also mechanical weathering, which takes out large chunks of rock through processes like freeze and thaw or wind erosion and then grinds down the rock as it travels down rivers. The result is mud, silt, sand, or pebbles according to grain size. These soft sediments build up around the continents, giving us our second principle of geology, that older sediments tend to lay underneath younger ones. Hot water that ran through the sediments dissolved silica or calcium carbonate and then deposited it between grains, binding the grains together. Over millions of years, this compression and cementation turned the sediments into solid rock like shales, siltstone, sandstone, and limestone. These are known as sedimentary rocks. Look carefully, and you can often detect the environment in which they formed. For example, cross-bedded sandstones show how ancient currents shifted. Bands of mud inside a sandstone may indicate the ebb and flow of a tidal estuary. Conglomerates formed from pebbles cemented together may indicate an ancient beach or a river. They look almost identical to pebbly beaches and riverbeds we see today. And this brings us to our third geological principle: the present is the key to the past. If the features we see in the rocks are identical to the features we see today, it's a strong evidence that they were formed by the same processes. For example, when molten lava is cooled quickly, it forms round lumps called pillow lavas, identical to structures found in ancient basals. This principle was brought home to me about 40 years ago when I was working for a diamond exploration company in northwest Australia. Yes, this really. Our helicopter was coming down onto an area of rippling sand, and I expected a cloud of dust to come up as we landed, but there was none. But there, okay, Reptile, why, 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 hey, hi there, When I stepped onto the sand, it was rock hard. It turned out that the ripples had been formed when this sand was part of a shallow Precambrian bay over 1 billion years ago. If layers of igneous and sedimentary rock were buried very deeply, the pressure and heat was so great that they changed into the third type of rock, metamorphic. Over time, limestone became marble, shale became slate, sandstone became quartzite, mudstone became schist. The more pressure and heat that was applied, the greater the metamorphosis. The heat comes from reservoirs of molten rock rising from the upper mantle, rich in minerals. This intruded into weak points, often powerful enough to deform the sedimentary layers above. When the magma cooled and cracked, hot water surged through it, depositing minerals like silica and metals like gold. Metamorphic and igneous rocks are still being formed today, but several kilometers under the surface of the earth. There's a view there. Under the several there a radio The only way we can see rocks like these is if they have been uplifted and then the strata on top of them eroded away. Uplift and erosion, which takes hundreds of millions of years. So metamorphic and mineral-rich igneous rocks are predominantly found in the remnants of the Precambrian, in ancient areas known as cratonic blocks or shields. They re not only the oldest and most stable parts of the crust, they re also the richest in minerals. For a long time there was a paradox in this Precambrian world. Just like a real dawn, the sun was much weaker back then, so weak that the earth should have frozen over, and yet it didn't. Geologists have concluded that what kept the earth warm was a high concentration of methane and carbon dioxide, strong greenhouse gases. As the concentration of these fell, exacerbated by other factors such as continental configuration, temperatures began to drop and the earth went into an ice age. Not this ice age, the one with mammoths and saber-toothed tigers that began a mere 2 million years ago. We are talking about the mother of all ice ages that occurred over 700 million years ago, when almost the entire surface of the earth froze over. And because this has a high albedo, in other words, it's so very reflective, what little sunlight there was got reflected back into space. So the earth might have stayed frozen if it was my for one that so the halves there are my Over 100 million years, volcanoes under the ice continued pouring trillions of tons of carbon dioxide back into the atmosphere. This time there was no weathering process to wash it out, so the carbon dioxide kept accumulating until it reached levels 20 times higher than today. It acted like a blanket and trapped what little heat was coming in. That started to melt the ice, reducing the albedo and warmed the earth even further. Eventually the earth thawed out, and because Catu levels were still very high, temperatures continued climbing until the earth became a hothouse with average global temperature of around 70, about 13 higher than today. Coral reefs grew near the North Pole. As we all see throughout the Earth's history, this link between carbon dioxide and global temperature is so crucial that carbon dioxide has been called the Earth's thermostat. We are now in a period called the Cambrian. Most of the continents were once again bunched together into a supercontinent, this once called Gondwanaland, although by the start of the Cambrian pieces of it had already begun to break away. An ancient Ocene called the Iapetus was abducting under one of these pieces, the continent of Laurentia. Trillions of tons of sediment washed into the depression between the two crustal plates. The land was still devoid of life, but in the oceans life now flourished. Cambrian fossils show a huge divergence of body types, possibly because of rapid evolution, the so-called Cambrian explosion, or possibly because animals had evolved hard body parts, which fossilized more easily. During the next geological period, the Ordovician, the Iapetus Ocene closed. Laurentia collided with a smaller continent called Avalonia, and then the mini-continent of Baltica. The series of collisions threw up a huge mountain chain as big and impressive as the Alps today. The granite bulk of the continents and the thick band of Ocene sediments in between them were thrust upwards. Scotland, which had been part of Laurentia, was fused to England. Yes, to all Scots out there, I feel your pain. To all guys out to you, I there, your pay you, your pay where, or I go, I crazy, Connecticut was fused to New York, and a new continent called Euramerica was created. But as we'll see, it was pulled apart again hundreds of millions of years later. The remnants of this crustal collision can still be found in the eastern part of the North American continent and parts of northwest Europe. The rise of the mountain chain increased weathering because high-altitude rocks are more exposed and weather faster. And because Cotto is used in the weathering process, this reduced the concentration of Cotto in the atmosphere, lowered the temperature, and triggered another ice age. Unlike snowball Earth, this ice age lasted only a few million years. It was centered on what's now the Sahara Desert and covered much of Gondwanaland. The new continent of Euramerica was further north. As water got locked up in ice, and because water shrinks in volume as it cools, sea levels fell. Geologists think the retreating coastline had a major impact on marine life and may have contributed to the Earth's first mass extinction at the end of the Ordovician. As Cotto levels climbed again, they pushed temperatures back up. During the Silurian period, the Earth was once again a hothouse, and sea levels rose. The oceans covered Ordovician rocks that had been exposed and eroded over millions of years. Ordinarily, one layer of sediment gets laid down on top of an older one in sequence, but when the sea retreats or the land gets uplifted out of the water, that process stops. Seats may be exposed and eroded, even faltered and folded, over millions of years, so when the sea covers them again and lays down new sediment, you get what's called an unconformity, which leads me to bin Laden. In 2001, I was watching the news, and a video from Osama bin Laden was played in which he stood in front of a distinctive rock formation. I am not a sedimentologist, but the fuzzy image looked like a shale or a limestone sitting on top of an unconformity. Surely, I thought, the intelligence services can figure out where that is. And sure enough, a few weeks later, a geologist who'd done some exploration work in Afghanistan said he knew exactly where that was and passed the information on to the CI. From then on, bin Laden delivered his death to America speeches in front of a plainclothes background. But getting back to the Silurian is also notable as a period when land plants evolved and spread across the continents. A few 100 million years later, during the Devonian, sea-based insects and animals also started venturing onto the land, and fish became the dominant species of the oceans. The mosses and lichens of the Silurian evolved into bushes that put down deep roots and weren't dependent on surface water to survive. And so they expanded across the continents. And as they did so, they sucked out carbon dioxide from the atmosphere, and that once again cooled the earth. They from the cool well. It's possible this cooling helped contribute to a mass extinction in the oceans, the Earth's second mass extinction. The cooling continued into the next geological period, the Carboniferous, and with a cooler Earth came retreating sea levels. Shallow seas and swamps were left behind. The wandering continents of Gondwanaland and Euramerica came together again to form another supercontinent, Pangaea. West Africa collided with the eastern seaboard of North America, and the Appalachian Mountains, which had first risen during the Ordovician and been worn down, were again buckled and uplifted like the crumple zone of a car crash. Bushes evolved into the first trees, and huge forests covered the swamps. Fish that could use their fins as limbs to negotiate the roots and stems gained an evolutionary advantage in the hunt for food and evolved into the first tetrapods, four-legged animals that were the forerunners of lizards, dinosaurs, and mammals. The proliferation of plant life increased the oxygen content of the atmosphere. Because insects absorb oxygen through their skin, that allowed them to grow to enormous size. But as well as releasing oxygen, the forests also took in huge amounts of carbon dioxide in order to grow. Only that carbon would be released back into the atmosphere when the trees died and decayed. But during the Carboniferous, the vegetation sank into shallow swamps where oxygen levels were low and didn't decompose. After millions of years of compression and heating, these layers of wood and vegetation turned into coal seams. This paleomap of the Carboniferous in Europe shows how the shallow water coincides with the coal fields of Germany, Britain, Poland, and northern France. The falling carbon dioxide concentration cooled the Earth so much that it once again triggered an ice age. Sea levels dropped even further, and the Carboniferous swamp forests began to disappear. The tetrapods of the Carboniferous had evolved into a weird-looking clade of reptiles called Synapsids and were still a long time before the appearance of the dinosaurs. The supercontinent Pangaea was now so large that rain clouds rarely penetrated the interior, creating huge deserts. Offshore airing of smaller continents enclosed a sea called the Tethys that would have a profound effect on our economy 250 million years later. Algae and plankton thrived in this warm tropical sea. When they died, they fell to the bottom and got buried in mud. There was only a weak circulation system in the Tethys, a bit like the Black Sea today, so organic matter did decay in the stagnant oxygen-free depths. This buildup of organic sediment in the Tethys would continue for hundreds of millions of years throughout the next four geological periods, uninterrupted by mountain building or tectonic subsidence. Over time, the buried sediment got compressed and heated and formed sedimentary rock. The organic matter trapped in the mud was also heated and broke down into simple hydrocarbons, in other words oil and gas. The mud turned into shale, which is a flaky permeable rock. Meanwhile, on the other side of the continent was another stagnant sea covering much of what's now the western part of North America. Called the Permian Basin, it also collected organic matter buried in mud and sand that turned into shale and sandstone. This would eventually give us the oil shales and oil sands of the United States and Canada. Towards the end of the Permian, molten rock and gas from the upper mantle forced its way up through the crust in Siberia and released what's called a flood basalt. It poured billions of tons of carbon dioxide back into the atmosphere, pushing temperatures up again into hothouse conditions, and another mass extinction followed. This would mark the boundary of the Permian and the next geological period, the Triassic. In this mass extinction, 95 of the species on Earth disappeared. The Triassic is a rather boring period in geological terms. There was little mountain building taking place because all the continents were now joined into a supercontinent that stretched from pole to pole. Even though the sun was weaker back then, the high levels of carbon dioxide ensured it was way too hot for us at either pole. The hothouse produced featureless deserts, and many of the rocks from that period are characterized by red wind-blown sands. Most animals had gone extinct, so in the early Triassic there weren't even many fossils to make the period interesting. The mass extinction opened up opportunities for the survivors because every organism inhabits a niche, a specialist role which can exploit resources. So when a lot of niches are suddenly opened up, animals will evolve to fill them. One of them was a tiny shrew-like burrowing animal that gave birth to live young and suckled them, the ancestor of all mammals. Another was an animal called the archosaur. The Triassic ended with another mass extinction, although the cause of this is not yet well understood. The archosaurs survived that one too. So when niches opened up at the start of the next period, the Jurassic, the archosaur filled them by evolving into the most famous ancient animals of all, the dinosaurs. During the Jurassic, Pangaea began to break apart. A rift opened up between Norway and Greenland, and then the eastern seaboard of the United States pulled away from West Africa. This was the birth of the Atlantic Ocean. In the western part of the Tethys Sea, Europe was just a patchwork of islands and crustal plates. Thick layers of limestone built up in these shallow seas millions of years later, providing the building material for Europe's great cathedrals. The limestone was also important for another reason. The rivers of resources for so to in the Tethys Sea, a constant stream of organic material had been buried in mud since the Permian. As limestone and sandstone piled up on top, the pressure and heat turned the organic material into oil and gas and the mud into shale. The oil and gas worked its way up through these permeable and porous rocks until it hit impermeable rock in folds and along fault lines, unconformities, and salt domes where less dense layers of salt laid down by evaporating seas move upwards through denser rock. These places where oil gets stuck, because it can't move up any further, are called traps. Tethys look for them by bouncing sound waves off the rocks below. When they find them, the exploration drilling team goes in to see if the traps contain oil. And in the Mediterranean and the North Sea, that was me job. So why does the Middle East have so much oil? Not only because over hundreds of millions of years the Tethys was a stable collecting point for trillions of tons of dead organic matter, but also because the shales, limestones, and evaporites ensured that the Middle East was full of oil traps. It's in the rock formations of the Triassic, Jurassic, and Cretaceous that 70 of the modern world's oil is found. The plants and animals that formed this oil took their carbon dioxide from K2 in the atmosphere and, of course, buried it with them. So once again carbon dioxide levels fell, helped by the background process of chemical weathering that created the Jurassic limestone. The falling concentration of K2 lowered global temperature and took the Earth out of its hothouse. As Pangaea broke up, moisture and ocean winds penetrated the arid interior. Conifer forests filled with ferns spread across the islands and continents. The first dinosaurs to dominate this new landscape were the sauropods. Contrary to Hollywood myth, the Jurassic wasn't the true age of the dinosaurs. They really flourished during the next geological period, the Cretaceous. This is where we get Tyrannosaurus rex and lots of other familiar dinosaurs. The Cretaceous was also marked by a series of flood basalt events in India that poured trillions of tons of carbon dioxide back into the air. As K2 concentrations rose, so did the temperature. By the late Cretaceous, the Earth was in hothouse conditions again. I often hear people point to the Cretaceous hothouse as a wonderful time when dinosaurs flourished, when there was thick forest and warm weather at the poles. Wouldn't it be nice if the Earth was like that today? Well, yes. There were large areas of natural forest during the Cretaceous, just as there are today. And of course, with a warmer climate comes higher sea levels, exacerbated during the Cretaceous by crustal movement. During the Vcodec, warmer, my with no water locked up in ice at the poles, and with warmer water expanding, the oceans covered the Great Plains of North America and nearly all of Europe, the Middle East, North Africa, and Central Asia. In fact, the areas that cover most of today's farmland and population centers were underwater. So perhaps it's not a climate we do want to emulate. In these warm seas, tiny plankton called cachalothophores thrived. Their shells fell to the sea floor and built up a thick layer of chalk. This is so much a characteristic rock of the period that the Cretaceous takes its name from the Latin word for chalk. The outpouring of gases and lava led to falling dinosaurs numbers, and they were finally killed off by a huge asteroid impact, marking the end of the Cretaceous and the start of the Tertiary, or the Paleogene and Neogene, as they call it in the United States. It's likely the only surviving dinosaurs were smaller, feathered species that most researchers now conclude evolved into birds. For that many burrowing mammals that also survived, the world was now full of vacant niches into which they evolved. The herds of large grazing dinosaurs were replaced by large grazing mammals. The pack-hunting carnivore dinosaurs were replaced by pack-hunting carnivore mammals. But how do we know that one group of animals replaced another, or that one group of animals evolved into another? The answer takes us back to the basic geological principle that newer sediment overlays older sediment. Let's look at an analogy. Imagine there's a garbage dump outside Lincoln, California, which was started when the town was founded in 1890, about the time households began using telephones. Within a few years, broken or discarded telephones would be thrown into the Lincoln garbage dump in the same way dead animals fall to the bottom of the sea. Over time, other garbage piles up on top. As the telephone evolved into better and more efficient models, these got dumped on top too, above the older ones. Telephones dating from the 1920s are different again, so when they got thrown out they end up here, and so through the 1940s, 50s, and 60s, right up to the era of mobile phones. But even mobile phones are evolving, and when older models get thrown away, they get buried underneath newer models. So if archaeologists 20,000 years from now uncover this garbage dump, they'll be able to tell which telephones were older and which were newer, based on where they lie in the strata. So if the archaeologists found a pile of garbage elsewhere in California, they'd be able to instantly place it in the chronology based on the type of fauna they find there. Similarly, as a general principle, we get newer fossils lying on top of older wounds. So just like the phones, we can see small differences as these animals evolved over time. If I can date a rock which has a particular fossil in it, and I find another rock with an identical fossil thousands of miles away, then there a very good chance both rocks are of the same age. The breakup of Pangaea during the Cretaceous gave rise to another era of drifting continents and continental collisions during the Tertiary. India crashed into Asia, thrusting up the Himalayas. Africa collided with Europe, pushing up the Alps. The subduction of oceanic plates gave rise to the Andes Mountains and the mountains of New Zealand and Japan. This era of mountain building, chemical weathering that once again sucked carbon dioxide out of the air, which cooled the earth and sparked its fifth ice age, covering a period called the Quaternary. This is the short test of our geological time periods, just 1 minute before now on our time clock. It wouldn't even rate a mention, except for the fact that it's the period we happen to live in. Our ice age isn't a uniform period of cold. It's characterized by cycles called glaciations and interglacials. The transition is sparked by tiny amounts of warming and cooling, as the Earth's tilt and orbit regularly change the pattern of sunlight it receives. Normally, these orbital cycles make little difference to the temperature of the Earth, but during an ice age, even the tiniest amount of warming and cooling gets amplified by what's called positive feedback. That's because a little bit of warming can melt a little bit of ice, reducing the amount of sunlight it reflects, therefore amplifying the warming. The melting of the ice unlocks methane from frozen soils, and a little bit of warming causes the oceans to release carbon dioxide. Both are powerful greenhouse gases. During glaciations, much of the Earth's water is locked up in ice, and much of the water that remains in the oceans is cold, so it shrinks. During deglaciations, most of the melts and the warm waters expand, so sea levels rose and fell by several hundred feet between glacial cycles. Because of the regular cyclical nature of glacials and interglacials, a lot of posters on me channels seem to believe that the Earth's geological history consists of cycles. In nearly every case, it turns out that they are confusing different periods of geological history, so let's put this in perspective. This red dot represents the last 1,000 years on the bottom time scale, and here's the last 650,000 years, a third of our current ice age, comprising glacial and interglacial cycles. None of these orbital cycles affect the climate during your lifetime or mine. So, during your cycle, they re on a scale of thousands of years, and the next time they begin sending us back into another glaciation will be long after your great-great-great-great-great-grandchildren have been dead and forgotten by their great-great-great-great-grandchildren. And this is where the entire ice age stands in relation to the last 500 million years. In relation to our geological clock, it's just 1 second out of 8 hours, 2 million years out of a billion. For most of the last 500 million years, outside of these very short ice ages, orbital cycles have no discernible influence on global temperature, because the changes in insolation they produce are far too weak. As for continental drift, flood basalt events, K2 concentration, global temperature, solar irradiance, and other constantly changing features of the Earth, these don't follow regular cycles either in time or amplitude. But no need to go to the other extreme and say that the whole system is chaotic either. With the exception of flood basalts and continental rifting, the mechanisms which cause these events are pretty well understood. We know they follow basic principles of physics. We know that most of them are linked, and in some cases they are even predictable. So just to be clear, these glacial cycles aren't ice ages, and they don't represent the Earth's geological history. They are part of an ice age and make up just 1 minute of the 8 hours on our geological clock. It's a history that includes at least 5 ice ages, 5 mass extinctions, and hundreds of millions of years of hothouse. Our Earth has experienced a world of deserts, a world devoid of plant life, a world of ice, and a world of water. So here we are today at 1 o'clock in the afternoon in a warm interglacial that's a pretty pleasant place to live and has given rise to the civilization we now enjoy. And what of the future? Well, according to researchers, our interglacial should last about another 20,000 years, giving us a benign climate and stable sea levels for thousands more generations. Unless, of course, we stuff that up. But tens of thousands of years is the blink of an eye in geological terms. If we look tens of millions of years into the future, Australia will continue drifting northwards, Africa will close the gap with Europe and squeeze out the Mediterranean Sea, and the 2 American continents will separate. 250 million years from now, our mountain chains will have worn down, new ones will have risen, and all the continents will be fused into yet another supercontinent. This will be 3 o'clock in the afternoon on our geological clock. Will our species survive until then? Well, the dinosaurs lasted 160 million years before going extinct, so if humans can survive as long as that, the answer is no. We want to be around 250 million years from now, but perhaps geologists of this future world, whatever they look like, will develop the same technology we have to delve into the past. They'll notice a sharp rise in carbon dioxide, accompanied by a sharp rise in temperature from our geological period. But this time there want to be any flood basalts to explain it. They all dig through rocks uplifted and eroded over hundreds of millions of years and find evidence of a sea level rise that buried strange geometric stones. They all see signs of the Earth's 6th mass extinction and a sudden disappearance of forests. All this in the blink of an eye, 0.5 seconds on our geological clock, which is actually 200 times faster than the blink of an eye. And from time to time, since land fossils aren't as well preserved as marine fossils, these future geologists will find bits of fossilized bone in the ancient rock that suggest the presence of some kind of upright primate. They'll no doubt wonder if there's any link. You